From Chicago, welcome to 3Degrees Discussions. I'm your host, Mike Vasquez. This is a podcast devoted to the stories behind the innovators, entrepreneurs, and leaders in the 3D printing industry.
There's a few different parts of hot plate welding. There's the cold tools. So that's the two halves that you're putting your injection molded halves into to hold them in place, right?
Okay.
And then there's a hot plate weld, or there's a hot plate that's 550 degrees Fahrenheit plus that comes from the back of the machine to the front of the machine. The two halves then come and touch off on that heat plate for a certain amount of time. Then they release off that. The hot plate flies back to the back of the machine, and then the molten joint or the molten weld rib of both halves come together under force and then cool and re-solidify into a full tank.
That was Andrew Roderick. Andrew is Senior Applications Engineer at Extol. Extol is a manufacturing technology company that improves the way plastic products are made. They provide plastic assembly technology, custom automation, and engineering services. From humble beginnings in 1985, Extol has become a recognized supplier of high-quality, standard, and custom plastics joining equipment. Approximately 90 employees work in their 53,000 square foot facility in Zeeland, Michigan. Andrew joins the show today to talk about their use of MJF technology and gives me a lesson on a variety of ways that plastic parts can be joined together to make seamless assemblies. Before we get started, head over to www.3degreescompany.com and subscribe to the podcast. Remember, you can subscribe to the show anywhere you download your podcasts, including Spotify, Apple, Amazon, or Stitcher. All right. Andrew, welcome to the show today. I'm excited for the conversation. I think this is just going to be super interesting because it's not something we've talked about a lot on the podcast previously. So before we get too far into some technical stuff and the work you guys do, why don't we just start at the beginning? Kind of where you're from, kind of what got you into kind of the path you're on right now.
Yeah, awesome. Thanks, Mike, for having me. I'm honored to be on the podcast. So, start at the very beginning. I was born in Wisconsin. I lived there for a year and then moved.
Packer fan?
No, I'm not. So I was just there for a year. So I claim Michigan. We moved to Michigan when I was one. So I don't remember Wisconsin.
A Lions fan?
Really? I guess I'm not. I don't follow football too often. I enjoy watching it, but I'm not tied to anybody. My feelings would be hurt, I think, more often than not if I did. So yeah, I grew up in Central Michigan. I always, in terms of like career path, I always was intrigued with architecture and building, different things like that. Both my grandparents or grandpas were in the construction industry. One taught shop, and then home building in the public school system. So I always had that path, and one of my other grandpa was like, "No, you need to do something that you don't have to be outside during the winter." And so I was like, "Oh, cool, architecture." And then about my senior year of high school, I have a cousin that's a dentist, and her husband's an engineer, and they were both trying. I was, kind of going back and forth on what career path I wanted to take, and they both started fighting if I should be a dentist or an engineer. And I really liked math, and so mechanical engineering is the route that I took. So I went to school at Andrews University in Berry Springs, Michigan. And yeah, started down that engineering path. Still really wasn't introduced to 3D printing much to that point. We did have a ceramic printer in the engineering department, but every time I touched it, it seemed like it broke. I actually had to outsource my printing project for that class because our printer was down. So it's still like I didn't have any interest in it, I guess, at that point. I just really wasn't it sparked my interest yet, right? And then later on, I think it was 2013, my buddy and I entered the Stratasys Extreme Redesign Challenge, and we won that. And so that was like
what was involved in that?
So that was basically they wanted you to take an ordinary object or an ordinary product and redesign it. So it didn't really have anything to do with 3D printing. It was just sponsored by Stratasys. Like we didn't have to design for additive or anything like that. So the idea was a seat or a crawler for like the automotive work that then folds up into a seat. And I think you see them around these days. I hadn't had that experience or seen them when we came up with it. So as like part of the winning, right, they sent us a 3D printed model of our design. So like that was the first like SLA print that I had in my hands. And then I had an internship at a custom automation company. And that's kind of where my career path started to go down the custom automation route. Had an opportunity at Extol to interview for tooling design, custom automation. I saw a lot of possibilities within one roof at Extol because of the many different business units, a couple different career paths. And so I started out as a design engineer for tooling, and then went into custom machine design. So robot cells, simple up-down presses, different things like that. And then there was an opportunity within the company. It was called the Garage. So one of the owners started up the Garage. It was a skunk work type mentality, and I applied for that. And the two of us, just blue sky ideas, trying to figure out what was next for innovation at Extol. And that's really where the love of 3D printing came into play. We had a Mark Forged FDM printer, and then right when I came into the new department that we were developing, right, we got a Formlabs SLA printer. So just being able to like get my hands into it, and just the joy of not having to design for CNC. My past, it was all plates, square blocks, different things like that. And being able to really open up the possibilities with additive. So that's really where the love of additive came in. And then a couple years later, had the opportunity to help bring additive into Extol in a bigger way, starting our additive business unit.
So one kind of first question for a lot of listeners who may be new to kind of the manufacturing industry generally, or kind of come across a podcast, like when you say tooling, like what do you mean by that? What does that entail in your mind?
Yeah, so we have a product called InfraStake. It's a heat staking assembly technology. So think of a plastic boss or post, and then another part goes over that post. You heat up that post, and then you mash it down like a plastic rivet. You can kind of think it as. And so tooling would be, think of like a door panel assembly line, right? I would design all of these modules, right? Or InfraStake modules that are going to do that heat staking to a specific customer's part. And then that would be integrated into the larger assembly machine.
Okay. And for kind of people who may not be familiar with like Extol, the company, kind of what's kind of the main business of the organization? We'll get into the 3D printing part in a few minutes, but kind of broadly, what does it do?
Yeah, so Extol started just over 30 years ago as a custom automation shop. So a customer could come to us with a product and say, how do we automate the assembly of this product? So whether that could be sheet metal bending or this or that, putting different components together to make a final product. And then in around 2008, we started to specialize more in plastic joining. And that's where, heat staking, hot plate welding, spin welding, all different manufacturing technologies to put two plastic parts together. So think of your chainsaw fuel tank, right? Or something like that, where those are injection molded into two halves, and then we're hot plate welding or heating a joint up and joining those two halves together. So when you look at it, I mean, I'm jumping ahead a little bit, but when we look at additive, right, you think about oh, you can print everything in one piece, right? And at first, being a plastic joining company, that was a threat, right? Are you not going to have to join plastic parts? But the more that we got into it, the marriage between traditional manufacturing and additive opens up a whole new world of opportunity.
I suppose, I mean, that's really kind of blowing the lid off of design for additive, right? Where you can think about the ability to weld two plastic parts together. And so that's something I've seen, and I can kind of conceptually understand what's going on, but why don't we just start there? Like what is plastic welding? Maybe even look at something like an MJF part where you're using like, I don't know, nylon or polypropylene or something like that. How does that work in the context of what you guys do?
Yeah. So taking a step back, right? One other reason that we added additive to our portfolio is to better help our current customer base across the whole product life cycle of their product, right? So we have a applications lab that helps them spec out design and different joint designs for manufacturing. We have the assembly side to put their parts together. And additive just kind of helps on the front end of functional prototyping as well as bridge production, on the back end. So when we think about, an additive project going further with traditional manufacturing, say, let's go hot plate welding, for example, with polypropylene. So we have customers that the traditional workflow, say for a fluid reservoir, right? Whether it's a fuel tank, whether it's a brake fluid, whether it's a coolant tank, some sort of tank to hold fluid. Their traditional workflow would be to commission a prototype tool for injection molding, mold, say, 100 parts, and then they would send us those halves, and we would hot plate weld them together, do burst tests, different things like that, weld joint development. With MJF and the new requirements for EV vehicles or different things like that, right? Our customers are looking for lower and lower volume prototypes to have better design efficiencies and a tighter design loop, right? So we're able to print those two halves of that reservoir and then hot plate weld them and do the testing in polypropylene. So we're doing the same workflow, but it's all in-house at Extol, and you're taking, 7 weeks, 10 weeks out of a prototype tool and able to print it in, days.
Can you describe a little bit about how hot plate welding works? So like, say you have two halves of a tank, kind of where's the heating source? Like, how do you get the polymer flowing enough to weld it together?
Yeah, absolutely. So there's a few different parts of hot plate welding. There's the cold tools. So that's the two halves that you're putting your injection molded halves into to hold them in place, right? Okay. And then there's a hot plate weld, or there's a hot plate that's 550 degrees Fahrenheit plus that comes from the back of the machine to the front of the machine. The two halves then come and touch off on that heat plate for a certain amount of time. Then they release off that. The hot plate flies back to the back of the machine, and then the molten joint or the molten weld rib of both halves come together under force and then cool and re-solidify into a full tank. So Extol was one of the first to have a servo-driven hot plate welder. So you have really, really fine adjustment and, a wider process window versus, say, pneumatics or, that sort of thing. So, but that's how hot plate welding works. So you're touching the part off onto a heated metal plate.
Got it. And was there any difference that you saw when you started working with MJF for 3D printed parts versus injection molding parts that you had worked with previously?
Yeah, so we did a direct comparison between an injection molded design and that same design printed in polypropylene on the MJF process. And what we found was we were still able to get a hermetic seal. We were still able to get parent material strength, which is basically breaking the part away from the weld. So saying that the weld is stronger than the actual material itself, or geometry around that part. And then in terms of burst pressure, we did have about a 20 to 30% reduction with multi-jet fusion parts. So that was due to not having pressure, right, in the process. So with injection molding, you're injecting that plastic under pressure. You get tighter bonds. With MJF, you're just melting it without pressure, right? And so I think that's the main difference. But
so that's not necessarily the seal's fault, right? The seal's probably fine. It's going to fail in somewhere else because of porosity or some other failure mode, versus the seal's going to be essentially the same. But
correct.
Okay.
Yep. So that's where we talk about parent material strength. The part might break in the same spot for injection molding and additive, right? Maybe around a sharp corner or something like that, right? There's a stress concentrator, but it's just a different burst pressure, a lower burst pressure with multi-jet fusion, and it's just a different manufacturing process, right? But for the most part, our customers, like, when we talk about that 20 to 30% reduction, it's like we can thicken up walls, we can do different things to design to be able to increase that pressure. But for the most part, we're just accepting that, and it's still works for their application, at least in the prototype stage.
So is there some fine tuning of that process where, like, as you heat it up, you have the hot plate in the middle, it releases, you stick them together. How do you not make grilled cheese, if you know what I mean, where you have like the pressure pushes out some of the material?
Yeah, so that's all in the tooling design of that fixture of how. So we're trying to support underneath the weld rib and as far up as we can on the wall, right?
Okay.
So it's being supported by 3D printed tooling, or in a production setting, it'd be aluminum tooling.
Okay, got it.
Does that make sense?
Yes. Yeah. No, it's a really cool process. And so do you have then, as you've done more of these types of iterations, like, is there a minimum wall thickness that you feel comfortable with doing something like that?
So there is a little bit of difference that we've found in how much weld rib we need. Mm-hmm. So if we needed like a 2 millimeter height weld rib on an injection molding, we might need a 2.25 or a 2.5 millimeter weld rib, just to take up some of the variation if there's warp in the parts, or if there's a little bit of cupping in the 3D printing. That just gives us a little bit more process window for running the parts. So.
And I suppose the big advantage versus, like, so if you come to me and say, like, how would you join two 3D printed parts together? Like, the obvious question is like, well, you could glue it or put some epoxy there. But with this, you're kind of keeping the material constant, and not introducing some other element or some other material into it. But are there what are the other kind of advantages that you'd have over, like, the adhesive route, or are there other ways that people kind of join these materials together?
Yeah, so that it all depends on what the requirements are from the customer, right? And so there's a certain sweet spot for quantity, right? Because we're going to have to design the tooling for the hot plate welding. So there's, I've done it where a customer needed one good part, and we did hot plate welding and spin welding, but they were trying to validate for production, right? And so they had tried it with glue. The assembly had burst under pressure into multiple different pieces, almost safety hazard kind of thing, right? And so they're like, okay, no, we're gonna do this right. And so we did it with hot plate and spin welding for that specific example. But like for a really, really low pressure, adhesive is going to be your most cost effective. But a lot of times in these kind of situations, our customers are trying to prove out the manufacturing process as well as the design, right? So if they're going to hot plate weld these in production, they want to do all their testing with a hot plate welded prototype. And some of these, right, these are some of our reservoirs that we've done for our customers are on mule vehicles that are operable and on the road. So it's a, it's that higher level of confidence and just quality of joint.
And I suppose it also increases the capabilities of the printer itself, right? Like when you think about size constraints of most 3D printers, right? Like it's 300 by 600 by 300 or somewhere in that range in terms of millimeters. And so now thinking about, hey, I need something like a tank or something really long, like you have options to put those together. You have to think then about the tooling and whatnot, but it just seems like you have this added layer of potential design freedom with additive.
Yeah, and for sure, the other thing to note, right? Like the glue is more of like a customization side, right? Like complex geometry, multiple different, axes and different things like that don't really work from a tooling standpoint or from a hot plate welding standpoint. The other one that we played around with is extrusion welding, and that's more of a, it's almost a handheld FDM. Really is what you can kind of think of it as. So that gives you a little bit more flexibility, but then you're also introducing polypropylene to polypropylene, and you're getting a stronger weld than just a surface level glue.
And so you mentioned like you had an upward limit of, I can't remember, it was like 500 and some Fahrenheit, which is 230 Celsius. So can you do higher temperatures like a nylon? Do you get enough flow? Or like, obviously you're not getting into like peak or Ultem or anything like that, but so nylon area.
Yeah, so we can definitely go higher. Nylon, we try to stay away from hot plate welding with nylon just because of the stickiness of the material. So releasing from the heat plate is kind of a caution, right? So we try to stay away from that a little bit. Nylons normally go into like vibe welding or ultrasonic welding, different things like that. So vibe is in vibration welding.
Yep. And so can you talk about maybe kind of pick a recent project that you've done that you want to kind of talk about or share some of the details on?
Yeah, sounds good. And I was thinking too, take a step back. So when additive became a bigger thing at Extol, right? We brought in 3HP 5200s. We're running PA12, the BASF TPU, and polypropylene. So those three different materials are kind of niches in different areas, right? So when we talk about, say, a recent program, we're a custom automation house. We do robot cells, right? And with every robot cell or any machine, there's always work holding fixtures to hold the customer part in place. So we use PA12 a lot for that. We just had a recent robot cell that had a turntable and ultrasonic welding, clip driving. There was just all sorts of things going on with that. And we had 150 3D CNC'd components that we were able to replace with MJF. And so with that, right, you've got end of arm tooling, you've got fixtures, you got different things. And with that project, we did PA12. We also did vapor smoothing on that as a little bit more of to protect the customer part from scratching. And we're about to do another set of tools for that same machine that we're going to incorporate TPU as like more of a poured urethane replacement. So there'll be a thin TPU on top of all the fixtures that are vapor smooth with a PA12 base. So with that project, right, we were able to reduce lead time. So normally it would have been like 4 weeks to machine all those details. We were at 10 days for printing, and then cost-wise, we came in about 50%. So $40,000 fixture project, CNC'd and all was about 20,000 with printing. So huge cost savings. You know, it was interesting. There was some really, really large parts that I wouldn't normally, like if you were to bring this fixture that's like this big to me just by itself, I'd say, no, go CNC that, right? But with the whole package, we were able to do nest those large parts with smaller parts, medium-sized parts, and the whole package, be able to save money with that quantity and different sizes and shapes and different things like that.
So as you've gotten more familiar with the MJF technology and kind of pertaining to a lot of the work you're doing with automation, like what's the sweet spot? Like what sorts of parts do you like say like, okay, like that's going to be a winner? Like, is it based on volume? Is it based on kind of how big the parts are, geometries? Like, are there kind of red flags that you see as someone that's kind of taking in, ingesting, and seeing a lot of parts and potential projects that you've kind of built to your own model of what's going to work, what's going to be a good project?
Yeah. So, I mean, it really, like I said earlier, it all comes down to the customer's requirements, right? Extol takes a different approach than most service providers in terms of we don't have an online portal to upload files to get an instant quote back. We have applications engineers that are looking at every single project like myself. And with that, right, understanding cost targets, understanding a customer's, current situation, what their hurdles are, is it lead time, right? Lead time can be a huge advantage for additive, even if cost is in line the same or a little bit higher, right? If we can get a little bit faster, that's a win. Sometimes it's just cost, right? And in those kind of cases, if you're doing a lot of parts, I would say the small to mid high complexity parts are the sweet spot with MJF. But if you have a package that has a big range of different sizes that you can, nest it. Think of the build box as like a jar, and the analogy of putting rocks in, then pebbles, and then sand. Those are, the more we can fit into that build box, the more cost effective all the parts in that build box are. But typically, I would say small to mid-sized parts with higher complexity. If you're trying to compare apples to apples.
Did you guys have to come up with your own kind of cost model as you were? Is this still kind of within the garage, like, or is it kind of its own separate thing now?
Yeah, no, it's its own separate thing. So when I was in the garage has now become more development and innovation. And I was a development engineer in that for a bit. But now the MJF 3D printing is in what we call our digital development center, and that's its own business unit with just those 3 machines. So Extol as a whole, I think we have 8 or 9 benchtop, FDM, SLA printers scattered throughout the company in different business units, but we're focused just on the MJF parts.
Okay. And how big is the team doing all of that work?
Yeah, so we've got, let's see here, 1, 2. So we got like 5 people in operations, and then 2 to 3 on the sales and management side. So we're about an 8-person team in the additive space.
One question that I've, as kind of the year closed last year, and seeing just reflecting on some of the work that we were doing and talking to different manufacturers around the country, is like, when it comes to 3D printing and kind of the work that you do, I mean, you started kind of the mechanical engineering path, but you touch so many different projects, and you have like this way of thinking where it's like you're combining processes and multiple materials and multiple ways of thinking and designing. Like, how do you, as you kind of grow your capabilities, grow your team, like what are some of the things that stick out in terms of the mentality that people have that are successful in kind of delivering on customer projects, or what skills maybe have you gained over the last few years that have helped you to become better at the work you're doing?
Yeah. So it was interesting in your last podcast, you were talking about, how do you get to where you are in additive? And I really think that it's all about being curious and just going along that journey and learning as you go. The more different technologies that you soak in terms of understanding how additive works, the more you can, disseminate that to your customers. We only have MJF, right, for our customers, but if I see a customer project that's not right for MJF, I'm going to tell right? And just be like, nah, this is probably an SLA part, right? Or is there slight tweaks that we can do to make it an MJF part? But it's really just a thirst for knowledge and being willing to adapt quickly, and learn as you go. I think are the main like factors or keys to success in the additive industry at this point.
So, kind of being in Michigan, located in kind of the Michigan area, you've mentioned some of the EV automotive based projects. Do you see that really driving kind of forward in terms of the automotive sector, like the electrification of vehicles, and so some new designs, lightweighting? Is that are you seeing that really grow with the incorporation of technologies like 3D printing?
Yeah, when I look at it, there's a lot of sexy applications for 3D printing out there. It's like the use cases that everybody uses, right? And I really think that there's a huge gap in the market for functional prototyping, right? We've used 3D printing for a long, long time in the prototyping world as fit finish, kind of just validation. But with the coming out of like these higher thermoplastic materials like polypropylene for MJF, or nylon in some cases, TPU for more flexible applications on vehicles, I really think that there's a sweet spot in having more functional prototypes that can go on cars. I see that as the biggest or the next thing, I guess, for automotive. There's definitely smaller programs, right, that could utilize additive as end use production. But right now, I think the key area would be more in the functional prototyping and being able to treat these printed parts as close to injection molding and do traditional manufacturing with them to get, because in the EV world, right, it's a whole new platform, right? So when you have automotive makers that have been doing internal combustion, year after year after year, right? There's normally surrogate parts that they can pull from one program to another to get that new vehicle on the road. But when you take an EV, well, there's not a lot of inventory or things to pull from, right? And so having higher functional parts for those seems to be a really key area.
And I don't know if I'll ask this in the right way, but I guess from like additive has struggled over the last few years in terms of that kind of convincing people to go from the prototype into production, or even going prototype to functional prototype. In the conversations that you've seen, like, what are some of the factors that lead to kind of taking that next step in terms of just beyond prototyping? Is it a personality of your customer thing? Is it, I'll get in trouble for saying, is it an age thing? Is it like, haven't seen enough, like I've used this at college and why not try it here? Is it a price? Is it a functionality? Like, what kind of combination of factors that you've seen for adopting additive in some of these applications?
Yeah, I think you hit on most all of them. I don't think it's, there's certain ones for different customers, but change management, I think, is probably one of the highest, where these customers' systems are set up for injection molding and like releasing products in that way. And additive is just different, right? So like how you fit parts in a build, how, like, if one part changes, it's more the build cost that you're dealing with. So all of the little parts, now that you've changed price of one, that disseminates into all these other ones, all these commodities, right? So like a whole project might be 5 different buyers within one company, right? And so having top down, bottom up change and willingness to adapt additive and go through that struggle to get it through systems that aren't made for additive, I think is going to be a huge challenge, at least in the automotive world, right? For other things, I think you can put a sample in customers' hands and all of a sudden it'll click, in a lot of, more of that smaller company size where it's like, 3D printing is for prototyping, you throw them apart. And it's like, oh no, we can use that. Like that'll work. Right. And so, and I think too, it's different options, right? So I had one customer in the automotive world that had a part that I could fit one part in the build from bottom corner to top corner, right? And I was like, yeah, I can print it in one. But then they came back and they said, we need 48 sets left hand and right hand in 2 weeks. And it's like, well, I can't do that there's not enough time in the day. And so when we look at that, it's like, well, I can't split it. And I came back to him and I said, well, here's 3 or 4 different ways that we might be able to do this, right? Can we add material here, right? Is this gonna interfere with any of your other components? No, we can add material there. Okay, how about we dovetail and we dowel, and then let's melt the plastic so that the dowel stays in there so we don't have to worry about glue or different things like that. Or is it glue and hot staple, or is it this, or is it that, right? And you give them 3 or 4 different options, and you throw out price and lead time for a full part versus a split part, right? And it's like, oh, so you're going to save me this much time, you're going to save me this much money, and you're delivering a joint that's going to be strong, like stronger than any other part of the part, right? Like the joint's not what's going to break. And we've had really good success with that on early prototype builds that go on vehicles. And so, the traditional adage of being able to combine parts for additive, right? So let's combine 5 different parts into one assembly. I think that works really well in the, high-end applications, say the metal assemblies, the fuel, the aerospace, the, different things like that. We've seen really, really cool examples of that. But what we're seeing a lot with MJF is splitting parts is more cost effective than having a bunch of parts put together.
Interesting. And so that brought me to an interesting thought. So as you're designing some of the assemblies to go together, do you do any different design on the edge? Like, would you make a lock and key and then melt it in to kind of strengthen that bond, or do you not need to do anything like that? Or does that even make it harder to put together, I guess, in some cases?
Yeah, so we actually did one sample part for AMUG last year that was for, we did extrusion welding on a reservoir. And with extrusion welding, right, you got to hold the 2 halves together, and then you got to, kind of have that hot tip go around, melt the plastic, and you're extruding hot plastic into that. And we actually did a snap feature between the 2 halves that's located and snapped it together. And then we were able to do the extrusion welding. So we have done, things like that where you incorporate like a snap feature or some sort of retention device, say a dovetail, to hold things in place while you're doing that more manual assembly process.
Okay. And speaking of AMUG, I think you mentioned that you guys will be there and maybe doing a session this year. So kind of coming up on kind of the last part of the conversation, how do people find out more information about you guys and what you're doing? And are there any things that are really exciting that people should check out in the coming year?
Yeah, absolutely. So our company website's extolinc.com. So extolinc.com. There's a lot of webinar content that we have on the website for additive. And then, at AMUG, we're going to do a workshop, and we're going to have a bunch of these different assembly technologies, not necessarily hot plate or spin welding of the larger machines, but staking, extrusion welding, hot staples, multiple different joining technologies as a workshop that you can come in and make some parts yourself and witness the technologies.
That's awesome.
So we're pretty excited about that.
Yeah, that sounds great. So Awesome. Well, I appreciate the time today and look forward to seeing you at AMUG and checking out the work that you guys continue to do.
Sounds good. Hey, thanks, Mike. Have a good one.
Thanks.